Let's learn about the globe embeddings. So globe embeddings is one way that converts words into vectors, which is nothing but a list of numbers, right? So that you can use in any machine learning algorithms, right? And it's an unsupervised algorithm where we don't need to give any training example. We just feed a bunch of words to the algorithm and it generates a unique vector that describes the relationship between the words. So let's understand how it does it. So this algorithm is developed by Chris Manning, Richard Socher, and Jeffrey Pannington at Stanford in year 2014. It mainly works on co-occurrence matrix of words, right? So what does this mean? Let's consider that our corpus has only two sentences. I like NLP, deep learning, and another sentence is I like badminton, right? Let's say we have only these two sentences in our corpus. Okay, then what we do is we basically compute a co-occurrence matrix as follows. So what we do is we plot the co-occurrence matrix like this. So here we draw words on column, all the unique words, and same words you draw on the row. Right? And then you decide that you have a window of 1, which means you describes how many times each word occurs to the next word. For example, the word I occurs with I one time, the word like occurs with I two times, the word NLP occurs with I 0 times, badminton 0 time, deep learning and deep learning 0 times, right? Similarly, how much times the word I appears with like 2 times, like appears with like 0 times, right? NLP occurs with like next to it 1 time. So we keep on plotting this co-occurrence counts, right? So this basically gives us a word vector itself, right? For example, we can consider this as word vector of I, then this as word vector of J, right? But what are the issues with this? So what happens is, uh, as your vocabulary becomes large, right, in practice you definitely have a lot more than two sentences, right? So what happens is your vector will become very large, right? And with lot of them will have zero values. So these vectors are called sparse vectors, right? So very often these sparse vectors are not used. Basically you use a technique like matrix factorization or suppose singular value decomposition to compress these columns into a smaller columns, which expresses the word into dense matrix, and it's called latent vectors because they may not describe, when you compress the matrix, they may not describe word to word relationship, but they can describe word to some category representation like sports, technology, and things like that, right? So the goal is to create the word vector, right? So this is very simple explanation. In practice we often use, instead of using a raw count, we often use the probability which is less than 1, and that can be normalized by using, for example, you can divide the probability of like by I by sum of all the probabilities of the word like with that occurs with every other word, right? So it can be 2 plus 1, things like that. So this value, overall value, will be less than 1. So this is probability that you express, right? So that's one intuition into globe. Okay, so what we do in Globe, so let's say xij is number of times the word I appears with word j. Okay, so the overall objective of uh, 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 Globe embedding is to generate word vectors wi and wj such that we minimize the loss, which is 1 to, let's say there are 10,000 words, j is equal to 1 to 10,000 words, uh, wi transpose w j. So these are the two word vectors we initialize randomly, and then we recompute the weights to minimize the loss, and then this is the bias term bi and bj, and then we use log of xij, which is the actual probability, and then we try to minimize the square loss. And then we often, so our goal is to compute wit wj so that this loss is minimized. Okay, so it's an iterative process. You can use algorithms like gradient descent to minimize those probabilities. Often this function is also multiplied with another function called f of xij. Why? Because you know that log of 1 is equal to 0, right? And log of 0 is infinity. So what happens is we define the function f of xij. It's a simple weighted function such that it is 0 when xij is 0, right? So that means when the f of xij of 0, it means basically don't bother compute the log xij at all. This whole equation becomes 0. Also for frequent words like is, this, there, this xij, this doesn't have any really meaning. These are just there to satisfy the grammar. So the f of xij is, the weight is very small, so that the importance of these words is reduced. Also f of xij will be very small for the frequent word, and f of xij will be large for infrequent word, right? So that it gives more important to infrequent words and reduces the importance of really very frequent word like is, this, the, and things like that. Okay, this is another intuition. So this is our overall objective. Another intuition of global vectors is this. So let's consider a case where now we will assume that we are using probabilities and not raw counts. So let's say you have a word like this: solid, gas, water, and fashion, right? And this is probability distribution, and let's say this is probability of K. Steam, probability of ice, so these are the raw probabilities, and let me just drop it, and then we'll have some intuition around this. Five. Okay, so in this probability distribution, you can see that ice co-occurs more with solid as compared to gas, right? That is expected. Similarly, steam co-occurs more with gas as compared to solid, right? This is very intuitive, right? Because those are the words, related words and related words. Now both of them, ice and steam, they co-occur frequently, I mean relatively equally with water, but very infrequently with the fashion, right? Now when you take a ratio of ice over steam, what we find that the difference between the discriminative word versus non-discriminative words is amplified. For example, when you take a ratio of ice over steam, of solid, the ratio is very high, and in case of gas, the ratio is very low, right? So wherever they are related, the ratio will be very high or very low. But in the case where they're unrelated, the ratio will be around close to 1, right? So by taking ratio of the probability, the difference, the discrimination of words with related words and unrelated words is amplified. So very often a ratio of probability is used rather than the raw probabilities. So this globe embeddings has already been trained, and you can download those pre-trained embeddings by just searching for download globe embeddings and go here. Then there are different globe embeddings are available depending upon the number of dimensions you choose. There, for example, here we have 42 billion words with 300 dimensions, and they have 840 billion words with 300 dimensions. So, but the size of the um, embeddings is large, and that's the accuracy is better. The larger the size, the accuracy is better. So you can start with a small model, and then you can start with the user bigger model depending on the accuracy that you want, right? So this is about globe embedding. So finally, when you draw the word embeddings, it appears something like this. So let's say the vector of the man will be somewhere here, vector of the word sir will be somewhere here, vector of the king somewhere will be here, the vector of woman will be somewhere here, madam will be somewhere here, queen will be somewhere here, right? So the interesting property that we observe with the vector is, for example, the distance of a man from woman, this distance will be approximately same as the distance between sir and madam and queen, right? That's an interesting property. So we can use any algebra property to derive the interesting vectors. For example, vector of king minus vector of queen should give you a vector which is very close to vector of a man, or vector of a or it should be vector of man minus vector of woman, right? Similarly, you can also do vector of king minus vector of man plus vector of woman. This should give you a vector which is very close to vector of queen. So you see how word vectors yield interesting properties that can be performed by using an algebraic equation. So we can always find the nearest neighbor. For example, the nearest neighbor of man would be a sir or a king. Nearest neighbor for woman would be madam or queen. Similarly, there could be countries like Paris, and England could be close, and maybe USA could be somewhere far, right? So these word vectors, by expressing them into embeddings, allows us to do an important nearest neighbor calculation. Also, it can be used for training deep learning algorithms that can help us doing more interesting pattern recognition like sentiment analysis, as well as uh, movie reviews and news classification and things like that.